All right, so might as well start. Today, again, we're looking at solving logarithmic equations. We're going to do that a lot today. Now, there's two situations that we're going to have, essentially. I broke it down. We're going to try to get to a log something equals log something. That is one scenario where we are going to call what's d log. Or the second situation we're going to have is you have a log of something and it equals a number. And so what we're going to do, and this is something we did a little bit before the other day, was switch to exponential form. All right, so I'm going to go through the examples here. So we get example one, we have log base 2 x. Said that wrong. It should be log of x with a base 2. Then we have 2 times the log of 5 base 2. And so we're not quite to the log equals a log because of this 2, but I can use my log rules that we went through the other day and put that log, or that 2, as an exponent on the 5. And now what I have is that situation where I have a log equaling a log. And so what I'm going to do is d-log, which essentially means get rid of the logs. They're gone. The log function's gone. Because what's happening is these two sides are on the same scale. And so because they're on the same scale, we can just break it down to the smallest parts, where we just now have x equals, what's in this part here is 5 squared. And so that means that x is equal to 25. All right, example 2, same scenario here. We have log equaling a log, nothing in front, nothing in front. So we can just d-log again, drop the logs. We're d-logging, I guess you could say. And so I have x minus 5 equals 10. Bring the negative 5 over to the other side, so it becomes positive. And we have a 15. 10 plus 5 gives us 15. All right, now, example 3. We have a log function equaling a number this time. And so what I'm going to do is switch to exponential form, which is something we have done already, which means, again, knowing how to convert a log expression into exponential. And again, there's your base, there's your exponent, there's your answer. And so I'm going to write it like that. So I have, there's my base, x, there's my exponent, negative 2, and there's my answer. So again, I just switched it to exponential form. Now I just go ahead and solve. So x to the negative 2, I could rewrite it as 1 over x squared equals 0.04. I always like to, when I got a fraction there, make a fraction equaling a fraction by putting that 0.04 over 1. I do that so that I can get rid of the fractions by cross multiply. And so I have 0.04 times x squared equals 1. All right, and then I can, I guess, divide both sides by 0.04. I'm running out of room here. And I get x squared is equal to, let's see here, 1 divided by 0.04. 25. All right, then I square root both sides. And I get x is equal to plus or minus 5. Plus or minus 5. But the thing with a log function is that what we found here are x. Your base always has to be a positive number. Your base and your answer have to be a positive number for the regular log function. And so we just have x equals 5 because our base can't be negative, and either can our answer be negative. All right, so there's 2 situations where we d-logged. Another situation where we switched to exponential form. All right, so just we'll get to example 4 here. Okay, make sure you do attendance before I forget. You get a chance. All right, example 4, what do we got? So, okay, example 4, we have 3 log x plus log 3 All right, equals 2 log 9. All right, so again, we're looking for the two situations. It looks like we're going to try to get a log equaling a log. We don't have that right now on either side. But what I can use is my log rules to try to make that happen. So first off, I got this 3 in front, and I have this 2 in front. So what I'm going to do is rewrite my first log here. I'm going to move that 3 and put it as an exponent, which some we're not used to doing. Usually we're doing the opposite of that. Because we want the exponent down in front when we're solving, but not this time out. All right, then I have the plus log 3. Again, I'm going to put the 2 up in front using my log rules. There we go. But I still don't have a single log equaling a single log. But I can put these two together. And again, using my log rules, if these two logs are plussed, I can rewrite it as log x cubed times 3, or properly written as 3 times x cubed. Just putting in a different order there. 9 squared. I can actually, that's 81, so I can actually figure that out. Now I have a situation where I have a log equaling a log. So I'm going to d-log. So I got 3x cubed is equal to 81. All right, now it's just solving for x. So I'm going to divide both sides by 3. All right, and let's see here. We get 81 divided by 3. What am I getting here? 27. All right, and then I have to get rid of that little 3. The only way to do that is to take the third root, both sides. All right, and the third root of 27, which means some number times itself 3 times. We'll give it 27. The answer is 3. 3 times 3 is 9, times another 3 gives you the 27. So again, I had to use some of my log rules here to get a log equaling a log. All right, let's see here. Example 5. Similar idea for example 5. So let's see here. Where we have log of x plus 1 with a base of 7. All right, plus the log of x minus 5 with a base of 7 equals 1. Oh, okay, so we got a number on that side. So the odds are what we're going to have here, or I know we're going to have, is we're going to have a log equaling a number. So we're going to eventually have to make that happen first so that we can switch to exponential form. So again, because these two logs have the same base and their addition, what I can do is rewrite this using our log rules. So I have the log of, now it's going to be x plus 1. Again, we can put these two together. So it's x plus 1 times x minus 5 base 7 equals 1. And now it looks messy, but I do have a log equaling a number. So I can switch to exponential form. And again, you have to be very comfortable with that, where here's my base, here's my exponent, here's my answer. All right, so let's write it like that. I'm going to switch it. So I got 7, there's my base, there's my exponent, and there's my answer. So I got x plus 1 times x minus 5. All right, well, 7 to the power 1 is just 7. Oh, I'm going to have a quadratic here. So let's see here, expanding it out. So I got x times x is x squared. And then let's see, x times minus 5 is minus 5x, but then I'm going to add a 1x, so I'm going to have a minus 4x here. And then 1 times minus 5 is minus 5. All right, so if I'm going to solve a quadratic, I need to get 0 on one side. So I'm going to move that 7 over. So I got 0 equals x squared minus 4x. Let's see, I got a minus 5. This 7 is going to be a minus. So minus 5 minus 7, minus 12. All right, so again, I'm looking at solving. So I'm going to try to factor here. Let's see here. So I got x squared, negative 12. Well, two things that multiply to give me x squared is x and x. Two things that give me 12. I got a minus 4 there, right? So I'm going to say it's minus 6 and 2. All right, so let's see here. Crisscross, minus 6x plus 2x. Yeah, that's minus 4x. All right, so I can factor this, or I have factored it. So x minus 6 is one factor. X plus 2 is another factor. And so now if I solve each piece, what makes that piece equal to 0? That would be x equals 6. There's an answer. And let's see here. Negative 2 would make that part equal to 0. All right, now I've got to check to see if my answers work, because again, your base and your answer have to be positive. So if I put a 6 in here, yeah, that's my answer will be positive. Put a negative 2 in here though. Negative 2 plus 1 is negative 1 times negative 7. That should work then. I believe it should work. All right, so we get two answers because it's a quadratic. X equals 6 and x equals negative 2. All right, let's see here. Next up, example 6. What do we got? Oh, this is a beauty. This one's a tough one. We need a whole board here. Now, example number 6 is tough because it takes experience to see this type of question, to identify it. So I guess that's why I'm showing you, just giving you some experience of seeing this type of question. And so what we got here for example 6 is, let's see here, 4 to the power of 2x. All right, plus 25 equals 10 to the power of, 10 times 4 to the power of x. There we go. Now, again, this is a type of a question that you have to be able to identify. The key here is that I know that really 4 to the power of 2x, I notice that that is really 4 to the power of x squared. And so what I have is kind of a hidden quadratic with an exponential inside of it. Weird situation. And that will happen as if you continually take math on and on and on, this type of situation. So because I'm identifying it as a quadratic, I want to get a 0 on one side. So I'm going to move this term over, and I'm going to rewrite my first term. So let's get that out of the way first. I'm going to rewrite my first term here as 4x to the power of 2. Because again, when you do a power of a power, you're multiplying. And then I'm moving this 10 times to the power of 4x over to the other side. So it becomes a minus. And I got this 25. Now, it kind of looks like a quadratic right now, but here's what I'm going to do. I'm going to make a substitution. I'm going to let y equal 4 to the power of x. So a substitution here. So what I have here, and I'm going to do this because it's going to make me to easier solve my quadratic and then further break it down into an exponential. You see what happens here. All right, so this 4 to the power of x, that's y. So this equation now is turned into y squared. Minus 10, and again, I'm going to call this y. Plus 25 equals 0. All right, so now it is a full-on looking quadratic. And I can factor this. Again, I'm going to have a little table here. I got my y squared, my 25, let's see here, y and y. Minus 10. It's got to be minus 5 and minus 5. Let's see. Those multiply to give me 25. Crisscross. Minus 5y plus minus 5y. That's a minus 10y. All right. So I'm going to have two answers. Actually, I'm going to have two answers twice, or the same answer twice. All right. So here's my equation. And so now what I want to do is I want to set each of these equal to 0. So I got y minus 5 equals 0. But since they're the same, I'm only going to do it once. All right. Now, here is where I'm going to sub that 4 to the power of x back in for y. So I'm going to do that over here. All right, so I'm going to have, instead of a y now, I'm going to put in 4 to the power of x. And that's equal to, minus 5 equals 0. And again, I just substituted back in for y there. All right, so then I'm going to bring this 5 minus 5 to the other side. So it's a positive 5. And again, this is something that we did last day. We're solving for the exponent, right? So what I do is I'm going to take the log of both sides. I bring that x down in front, again, using one of our log rules. The log of 5. Let's see here. Log of 5. Where's the log button here? There it is. Log of 5. I'm going to go with 0.7. Rounded to 2 decimal places. There goes 0.6989. Then I can find the log of 4. Log of 4 is 0.6. All right, then finally, going to have some room here. Divide both sides by my numerical coefficient here at 0.6. And my x value is going to be whatever 0.7 divided by 0.6 is, which we get 0.7 divided by 0.6, 1.17. And again, we have that answer twice because there's 2 pieces. So if these 2 were different, you would have to go and solve the second piece just like I solved the first piece. All right, but again, that's a tough question. One of those ones that is more of a, you got to have some experience with it and identify it. All right, next up, what do we got? Number 7. We can do them all today. They're all a little bit unique. It's nice and dry. All right. So example 7. And this is true. The Richter scale is used to compare the intensities of earthquakes. The Richter scale magnitude R of an earthquake is determined by the formula. There it is. Where A is the amplitude of the vertical ground motion in micrometers. T is the length of time the seismic wave lasts. And B is the factor that accounts for the weakening of the seismic waves. Pretty complicated stuff. All right. So then I'll get to the final sentence here. But I'm going to write down the equation because I have R is equal to the log of A over T. So I'm going to have to substitute in a lot here and find out what I need. All right, so now back to the last sentence. Find the amplitude, okay, of the vertical ground motion if an earthquake creates waves that last 1.5 seconds. So I believe that's my T value, 1.5 seconds. All right, has a weakening factor of 2.5. Which one is that? B. That's B. In the question, that's 2.5 is our weakening factor, and it measures 7.5 on the Richter scale. So I know that's R. Okay, and so we're looking for, what is it? A. There we go. That's what we're looking for right there. So the first thing I'm going to do is I'm going to substitute all this information in. So I have 7.5 is equal to the log of A, because that's what we're trying to find, over 1.5, plus B, which is 2.5. All right. So I believe in this situation, we're going to have 2. We're going to have log equals a number. But to make that happen, first I'm going to move this 2.5 over first. So if I have moving the 2.5 over, it becomes negative 7.5 minus 2.5. That's going to be a 5. All right. And so now what I have is a log equaling a number. And so again, when you don't see a log here, it has a base of 10. So I'm going to switch this to exponential form. And so there's my base. There's my exponent. There's my answer. So 10 to the power of 5 is equal to A over 1.5. And so if I take 10 to the power of 5, which is 100,000, 5 zeros. And so again, equals A over 1.5. That's an A. Kind of looks like a 9 there. A. Again, I like fraction equaling a fraction here to solve. And so I have A is just going to be 1.5 times 100,000, which has to be 150,000. And A, what are our units here? A was in micrometers. A is our ground motion in micrometers. There we go. Which is 1/1,000,000th of a meter. That's what a micrometer is. But again, just a real life situation where we sub in our values. And then in this case, getting a log equals a number to once again get it in exponential form, which we converted to solve. All right. That was example 7. Last one, example 8. All about the decibel scale, another logarithmic scale that we're going to talk about a little bit more later today, 10 o'clock. Logarithmic scale goes up, or the Richter scale goes up by ones. The decibel scale goes up by tens. All right, so example 8. In that the loudness of a sound in decibels can be calculated using the formula. So I'm just going to write it down because I know we're going to use it. L equals 10 times log of I over I naught, but I naught's got a value here. It's 10 to the power of negative 12. So I'm going to just plug that in right away. And what we want to know is determine the intensity of a jet taking off if the sound level is 120 decibels, which is just sort of making blowing out your eardrum. You get to about 130, 140, pop. But that's why those guys wear the big earmuffs on the jet tarmac. All right, so our loudness in decibels is 120. So that's our L value. So I'm going to substitute that in. So we have the log I divided by 10 to the negative 12. All right. And again, you can see, or I can see anyways, we're looking at a log equaling a number, but I got to get rid of this 10 first because I need a single log. So I'm going to divide both sides by 10. And so, well, 120 divided by 10 is 12 is equal to log of I over 10 to the negative 12. All right, and now I do have a single log equaling a number. And again, it has a base of 10. The Richter scale and the decibel scale always go up by factors of multiples of 10. All right, so now I'm going to switch to exponential form, which again means here's my base, here's my exponent, here's my answer. So I have 10 to the power of 12 equals I over 10 to the negative 12. Oops, there we go. All right, once again, I'm going to do fraction equaling a fraction. And so I have I, 1 times I is I. All right, and then I have 10 to the power of 12 times 10 to the power of negative 12. And, well, we have a power times a power. You keep the base the same, add the exponents, 10 to the power of 0. And it looks like 10 to the power of 0 is just 1. What's our units here? I is the intensity of sound in watts per square meter. So it looks like 100 decibel sound is 1 watt per square meter. And there we go. So there is solving logarithmic equations. We're going to do more of that at 10 o'clock.